This is week 5. We're discussing matrix operations for solutions of linear systems. There are 3 main row operations. One of them has to do with multiplying every term of the row by scalar. Here denoted as alpha times r sub j. There is the swapping, exchanging locations of rows. That's denoted with a double arrow, rk, double arrow, r sub j. And then there is something that's a linear combination where one of the terms has a coefficient or a scalar of 1. The row that's written last is the row that will also be substituted or replaced. So this is what appears here as beta rk plus rj. That means that after computing that row operation, the row r sub j will be substituted. So we have an example where there are 5 equations and 2 variables or 2 unknowns. Those equations are translated into a matrix that is a 5 by 3, a matrix with 5 rows and 3 columns, where the last column denotes the constants that are originally located in the right-hand side of the equations. So when applying row operations, the main goal is to create ones and zeros. We start by creating a 1 on position row 1, column 1. So we'd like to substitute here in yellow, row 1, column 1 appears with an entry of the integer value of 2, positive 2. And we can do this in a couple of steps. First, we do a row swap. Then we multiply the new row 1 by negative 1. And that gives a 1 on that location. Then we move on to create zeros in the first column. So specifically, we are interested in creating zeros in the first column in rows 2, 3, 4, and 5. So we'd like to do row operations to start creating zeros in that column. So we can see here that with the row operation minus 2r1 plus r2, we create a 0 on row and position 2, 1, row 2, column 1. Then we have a row operation negative 3r1 plus r3. That creates a 0 on row 3, column 1. And then we continue with the operation minus 3r1 plus r4. That creates a 0 in position row 4, column 1. Next, the operation negative 6r1 plus r5 creates a 0 on position 5, 1, row 5, column 1. So the next goal will be to create a 1 in position row 2, column 2, and then create zeros afterwards. And to do that, we can multiply the second row by the scalar. Whatever the number is in position 2, 2, or row 2, column 2, we can multiply by. So we can multiply by a fraction where the denominator is the non-zero value that appears in the location where we want to create a 1. So in this case, we're using the scalar 1 over 11 and multiplying the entire second row by 1 over 11, and that gives us the numbers 0, 1, and negative 2. Then we'd like to create zeros in the second column, but specifically in the second column below the entry where we just created a 1. So, so we look at the matrix in the previous step, and we'll look at row number 3, and we use the operation negative 22 times the second row plus r3, and then we substitute the third row. That actually becomes a row of zeros. Next, we would like to create a 0 on row 4, column 2. We're going to use this scalar multiplication, negative 11 times the second row. We can see what that is equal to, and so we do minus 11 times r2 plus r4. We're substituting the fourth row, and that gives us another row of zeros. And the next operation will be negative 33 times r2 plus r5, and that gives us a row of zeros on the last row of this matrix. Now, what we're going to do next, we accomplish a column of zeros, lots of zeros in the first column, lots of zeros in the second column. If we look at the first row, we can see that on row 1, column 2, there is an entry of negative 4. we would like to do something with that entry. And for that, we're going to use this operation that's specified here at the bottom in purple. 4 times R2 has values 0, 4, and -4. We're going to add that row to the first row, and then we're going to substitute. So we're going to do R4, R2 plus R1, substitute in the first row, and that gives us now a new row with entries 1, 0, and 6. The second row has entries 0, 1, -2, and then all remaining 3 rows are rows of zeros. So in this form, we would like to go back to the original. We are able to actually read information that's pertinent to the original system of linear equations. These matrices, every step of the way, we were applying row operations and we were transforming the original augmented matrix. All every intermediate matrix, each of them is still 5 by 3 matrix. Every intermediate matrix is representing an associated linear system. And so at this step, we have created as many ones and zeros as we can, and what we are going to do is read the corresponding linear equations that are specified by each row of this matrix. So the first row, remember, the last column represents the column of constants. RHS stands for right-hand side in the system of linear equations. So the last column represents all the values that the equations are equated to. So, and the numbers to the other side of that last column, they had a name. They are called, we had written this with some terminology here. So the last column is the column vector of constants, right-hand side of the equations. The other values to the left of that last column, they're a submatrix. It's called the matrix of coefficients. So those values that are to the left of the last column, they're specifying coefficients in the linear equations. So that's what we're going to do now. We're going to read this information and write it accordingly. So the first row has value of 1. So 1 is a coefficient of the unknown x1. That is a coefficient of 0 for the unknown x2. And then the value on the right-hand side is 6. So here we have the equation 1x1 plus 0x2 equals 6. This would mean that really we only have x1 equal a value there. x1 equals 6. That's one thing that is an implication of all these calculations. The second row has values 0, 1, and -2. 0 is a coefficient of x1, and then we have 1 as a coefficient of x2, and the value in the last column is -2. So that will be the value on the right-hand side of the equal sign. So this implies that simply we would say x2 equals -2. So this is also important information. So x1 and x2 are unknowns, and now this is specifying that there are specific values for each of the unknowns or each of the variables. Now what we have on all the other equations is several zeros. For example, row 3 gives us 0x1 plus 0x2, and that is equal to 0. This simply is saying that here that 0 equals 0, and that is, there is nothing wrong with 0 equals 0. That's perfectly fine. Okay, so now this is like a remark there, and then so of course it looks like some evil eyes looking at us, right? So, and then row number 4 would give us 0x1 plus 0x2. This is equal to 0, and then the last row number 5, would give us 0x1 plus 0x2, and this is equal to 0. So that is, each of those equations is given something that is, you would say, kind of trivial, but there is no contradiction. It's totally totally fine. So the challenge with equations, a system of equations or a list of equations, is to find values for the unknowns that satisfy all the equations, not a subset of the equations, but satisfy them, all of them. So once we have found such values, and we'll see later that is more about finding sets of values, but here we have the value of 6 for x1, the value of -2 for x2. The verification is kind of going and then plugging in these alleged values, these alleged solutions, plugging them into the equations and confirming that the left-hand side matches the right-hand side. So x1, if we look at the first equation number 1 here, so x1 is evaluated at 6, x2 is evaluated at -2. So I'm going to work here with the left-hand side. This gives us 12 minus 6, and I keep working with the left-hand side, and this is equal to 6. So this is the left-hand side, which matches the right-hand side of the equation. So this is a good match. So similarly, if we plug in the second equation, substitute x1 with 6 and substitute x2 with -2, we obtain -6 minus 8, which is -14. And this is matching, this is the left-hand side of the equation, which is matching the right-hand side of the equation. And is similar for equation 3 and equation. We're doing verification is a confirmation. So we're evaluating the equations at the solutions, at the values that are alleged solutions. So for equation number 3, we see this becomes 18 minus 20, which equals -2, and that matches the value we had there originally. For equation 4, we see that this becomes 18 plus 2, and this is equal to 20, and 20 is also a match. And for equation 5, when we evaluate 6 and -2, we obtain 36 minus 18, which is equal to 18, which also confirms that the left-hand side becomes the right-hand side with these values of solutions. So in summary, row operations are useful in transforming, let's see, where do we start here? We started with a system of linear equations. We created an augmented matrix. We applied row operations. The row operations are meant to create ones and zeros, and ultimately would like to be able to determine which are the solutions of the system of linear equations. And what we were doing there at the end was a confirmation or verification.